Well, let's finish the abstract nonsense today, and then we'll talk about applications and Tom isomorphisms next time. Okay, so more abstract nonsense. Let us show that not every object can be expected to be dualizable. Let's assume that that C has an internal Hom functor. Meaning, let's assume that we have a bifunctor f from C cross C to C, such that we have this functorially in all variables. In other words, we want to construct a right adjoint Okay, let me write it like this. So we have C left adjoint the left adjoint is censoring by Y, and the right adjoint is F Y F from Y. Okay, so the left adjoint applied to X, comma Z is the same as C, from X to the right adjoint applied to Z. So basically, we want to write a right adjoint of this functor, and if this right adjoint exists for every y and depends functorially on Y. In this sense, then we say that the category has an internal Hom. As we saw last time, modulo the representability theorem, the Hom spectra has an internal Hom. And we also have an internal Hom for vector spaces over a field, which is clear. And my claim that if X and Y are dual, then Y is isomorphic to the internal Hom into the monoidal unit. Okay, well, let's prove this. Okay, let's see. So we have just constructed an isomorphism no, sorry. No, we have constructed this isomorphism. What now? Well, this no, we want to prove that both Y and F XS represent the same the same functor. So this is what we want. Let's see. See if it works out. Okay, so this is the first equality is something we've just seen. And the second equality is something we want to prove. Well, let's start with the right-hand side. C of Z f s x. Oh, sorry, x s is well, it's isomorphic to C Z Z wedge S, S, and this is isomorphic by what we've just seen. Actually, okay, let me change x and y here so that we actually use exactly what we proved last in the first half. So we have this. I just replaced x with y and y with x, and in a minute we'll see why this is legal. But first, let's see where this leads. Where this, which is this by the adjunction, and this is the same as Z S X, and this is the same as C Z X. So let me. So we see that Fys and x represent the same functor. So x is isomorphic to Fys by the Uneda lemma. Does this make sense? Very well. Now let's see that if x and y if x and y are dual, so are y and x. In other words, if we take the double dual, we get back to where we started. Well, let's see. So y wedge x. So we have the evaluation map and the co-evaluation map. Let's is this let's see if it's the same notation I used in yes, it looks like it's the same. It's the same order I used in the first half of today's class. So, good news. Now, what do we need? Well, we need epsilon prime from y to x s and eta prime from s to x wedge y. And there's there's just one obvious candidate for eta prime. Remember that our category is not just monoidal, it's symmetric monoidal. So we start with y x, we swap the two factors, we get x, y. And similarly, so this is the old epsilon, and this is the old eta. So the obvious guess would be to just swap the factors and then we need to prove that the recipe works. Well, let's see. Okay, so let's check. So we need to prove two identities. Um, no. So we start with x, and then we no. Oh yes. So we create x y x on the left. And then we collapse y wedge x on the right, and the whole thing needs to be the identity. Well, let's see if it works. So, well, firstly, we need to create x tensor y on the left. How do I do this? I create y tensor x and then swap the result. So again, I systematically ignore the brackets and associators. So x wedge y wedge x. Okay, similarly here, I need to destroy y wedge x. What do? I swap the two factors and then destroy them. Okay, so this is the old x, the identity of x wedge the old epsilon, and this is the old eta wedge the identity of x. Okay, well, let's let's see. Let's write this composition again. So I go and as you've no doubt noticed, I also ignore the monoidal unit, which is S. So normally, I should before I create y wedge S out of nowhere, I should add S on the left, but I just don't do it. Okay, so let's rewrite the diagram and see if it gives what we want. So I go from X to YXX. Then I swap, so here I use eta. Then I swap the two factors. The first two. And then I make another swap. I have x, y, and I swap them to get I have y, x. I swap them again. X, x, y. And then I use epsilon. Okay, so there's an eta, there is an epsilon, but there are plenty of swaps. So what do we do? We remember the axioms of symmetric monoidal category. And we also remember these okay, so instead of going this way, I could do something something else. I could create so here I created y tensor x on the left, but I could create it on the right. So here here I created y tensor x on the right, then I collapse x tensor y on the left, and I get x. Okay, so my claim is the diagram commutes. Now, why does it commute? Well, it commutes because of the symmetry. Namely, using the associator and the symmetrizer, which are part of this symmetric monodal structure, we basically can identify all products which have all possible products which have two factors of x and one factor of y. So here we swapped something, and here we swapped something else, but so the diagram commutes because all ingredients which have two x's and one y can be identified. And as a consequence, we conclude that the straightforward idea of defining epsilon prime and eta prime works, and this is it. So as a result, corollary. if we have a category which is symmetric monoidal, which has an internal Hom, then two objects which are dual in some order are also dual in the opposite order. And each of them is the internal Hom of the other one to S, up to isomorphism. So, dualizable objects of vector K are precisely those vector spaces which are finite dimensional. And the natural question is, what are dualizable spectra? Well, let me state the answer. We will not prove it today, but we'll prove it maybe next week. Now, the dualizable spectra are precisely the finite spectra. Now, what are those? Well, the easiest way to define finite spectra is to consider CW spectra and then to require that there should be finitely many stable cells. Well, equivalently, a spectrum X is finite. Well, again, CW. Spectrum X is finite if if and only if it's the suspension spectrum of a finite CW complex, maybe with a shift. Well, in one direction this is clear. There are a finite CW complex has finitely many cells, so there are finitely many stable cells, and in the other direction it's also clear. Suppose we have suppose we have finitely many stable cells. Then each of those will be in some xn for some n, and we could take y equal xn and k equal, well, plus or minus n. So, finite spectra are precisely those spectra which are suspensions of finite CW complexes up to a shift. And the claim is that finite spectra are dualizable, and conversely, all dualizable spectra are homotopy equivalent to finite spectra. Now, we will, for the duality theorem, we will only need to know that if the spectrum, if we have a spectrum which is finite, then f of the spectrum into the sphere spectrum is also finite, meaning it's homotopy equivalent to a finite spectrum, and the double dual is the spectrum itself. This is weaker than being dualizable, but for our purposes it'll be enough. Anyway, we will talk about this next time, and the idea is very simple. Suppose we have a finite CW complex. Well, let's embed it in some sphere such that the complement is also homotopy equivalent to a finite CW complex. Then, up to suspension, the two complexes, the one we started with and the one which is homotopy equivalent to the complement, will be the duals of each other. And yes, let's talk about it next time. It's not very difficult, but it's not completely for free. So let's do it next time. Okay, are there any questions?